part on my screen is a great example. Without thin wall rolling, we'll see that a large thin wall section is going to be left and essentially machined away. And this can be detrimental depending on material types, that we could essentially kind of fracture off material and that cause some catastrophic tool issues. So with the new thin wall rolling option, we're able to roll around those thin wall regions and cut in a more controlled environment. Just a little bit enhancement for process stability. We also have an option called over machining. And what over machining will do is changes some of the corner rounding paths of our of the tool path that's provided. And the intent here is in different materials that we can get some deformation of the material as we're cutting geometry, that we can cut, kind of overcut different regions to make sure that we're really removing all the material as anticipated. Face mill mid-pass is a new operation type, and it's specifically intended for the types of parts that we're looking at right now. And that being any kind of a housing where we have, some kind of a mating surface, bolt pattern, flange type region. If you've cut these types of parts in the past, you're probably aware that it was never the easiest to get a very nice tool path on these types of geometry. Perhaps we want to mill right down the surface, or kind of cut just a basic convex hull type shape. So those are two options that we now have in this specific operation. So this operation is not intended to replace like a floor wall, a floor without wall operation. But it's really for a different type of intent here. So in this case, we can see that by specifying our cut area as this flange face and generating the tool path, we get a nice simple tool path right down the middle mid-pass of that surface to go ahead and kind of deck off that region. We have the ability to modify our geometry, in this case showing that we can ignore the holes to essentially cut around the whole geometry. Some cases you may want to do this. I think typically that's not how I would envision processing this type of geometry, but all users have a little bit different use cases. You might notice that we're also getting an active preview of what the tool path is as we make changes. So here's, as we change the pattern offset or change, reverse the direction, we can see how that is affecting the tool path that would be generated. The offset feature is very nice. Oftentimes we don't want to drive our face mill directly down the center of some geometry like this. We want to offset one direction or the other to, again, utilize some chip thinning principles for better tool life, better surface finish, things of that nature. We can also look at the resulting IPW. In this case, when we're offsetting around some of these regions, we can identify some uncut material. Just a quick graphical representation to see that, yeah, we would have to add some additional tool path to handle those regions. So talking about that preview that we had as we're changing conditions inside of our operation, we can of course change colors in our preferences for the operation, depending on company standards. What do you typically have your parts modeled? Maybe the colors are too similar to your parts. So we certainly have the ability to go ahead and change those colors as we're showing right now that we change to that magenta color for our preview. If we go ahead and I'll jump forward to the convex hull option. So we're going to change our part. And in this case, on this geometry, we'll compare the mid-pass option to the convex hull option. So right now we're driving right down the mid-pass of our geometry. If we switch the pattern type to convex hull, we're driving to the outer edge of that particular geometry. Again, we can get our path preview so we can see as we're making changes what is our anticipated tool path. So for the right types of parts, if you have these types of housings and a lot of flanges, I think this is going to be a pretty beneficial operation for you. Guiding curves and the new mid-pass pattern options. So I personally use guiding curves quite a bit in my surfacing operations. It's usually my go-to for any type of contoured surfacing with ball mills. And now we have two new operation types, two new pattern types. Mid-pass pattern, morphing around mid-pass, and offset around mid-pass. So the great thing about these operations is the mid-pass or medial axis of our geometry is going to be found by the software automatically. It's just looking at our cut area and finding this middle curve. So we don't have to specify as the programmer any actual guiding curve geometry. The software is going to do that for us. So the toolpath or pattern types are going to be driven off of a mid-pass. So here we can see, looking at this one surface, if we would cut just one path, so there's no real step overs here, we'll see that we're driving right down the center of that geometry. And so we have a new toggle option here under Drive Geometry, Extend Guide, to cut area edges. So the medial axis, by nature, doesn't run all the way to the edges of the curves, but this option allows us to extend all the way to the edges of our cut area, so we can feed all the way on and off of the part geometry. Very useful when we're doing an offset type pattern. So in this case, we can see that driving that mid-pass, we're going to handle offsetting from the top to the bottom of the geometry. When we look at morphing, we can see that it's really going to be the similar type of a pattern. And these options are now very easy to use in that we don't have to specify any guiding curves. However, they're not going to replace the existing functionality. Here we can see on this slide that a constant offset is a much simpler, nicer toolpath than using any of the mid-pass patterns. So by no means is it a replacement for the existing patterns, just more tools in our toolbox for us to use as programmers. The new turn milling operation. This is going to be part of the rotary milling template and will allow us to do some more turn milling type toolpaths. Great for eccentric features, radial features. I personally like to use this type of a process when I'm programming parts that might be run in an unmanned operation. If I'm thinking like a mill turn machine, that I could certainly turn a lot of these features. But if I want to have better chip control, this is a good opportunity to use a turn milling operation where we don't have to worry about stringers being formed, wrapped around the part, wrapped around our tool, potentially causing issues in an unmanned automated process. Additionally, some difficult to machine materials. A lot of times we can mill them a little bit more reliably than turning. This doesn't have to be a pure 4-axis type operation. We can certainly use a turn milling operation on a 5-axis machine at some non-orthogonal axis to create some really unique toolpaths. If you've used any of the newer operations, like rotary roughing, it's been introduced a couple, 3-4 releases ago. The look and feel of this operation is going to be very familiar to you. The way that we can limit geometry, both axial and radially, specify our step overs, engagements, are going to have that very same similar feeling. So here, basic engage types, orthogonal or tangential. How do we want to engage into the part? I think, in my mind, tangential is typically what I would use, feeding in, I guess if you're typical vertical with a 4th axis would be in the y-axis. But we can change simple parameters, direction, positive, negative rotations. The operation is very pragmatic and it's pretty intuitive in the various settings. So that's something I think Siemens has done a great job with in these new operations, making them pretty simple to use and easy to understand. That's not always the case with some of our more advanced 5-axis operations. So that brings us to the turning threads IPW. This is a little bit of a kind of a nice to have, in my opinion, but it's also crucial for some customers. We can see that with our new threading operations and thread inserts, tooling types, we now, starting in 2306, support the actual depiction of the accurate IPW of a turned thread. This is really great for a number of reasons. One, there's some cool factor involved that you get to see that thread being formed. But two, if you're working on large parts or features that's maybe difficult to inspect in process with your traditional hard gauging, you now have an accurate IPW that we could actually use a probe and probe the profile of our thread to check in process the quality of our thread and dimensional accuracy of our thread. So just something kind of forthcoming to see more of these strategies that can be put in place. Automatic toolpath generation is now supported for more of our operations. So in 2206, we started supporting automatic toolpath generation for all turning operations. We now have the same support or similar support for a lot of our curve-based milling operations. So things like planar milling, profile 3D, solid profile 3D, planar profile. So we can see as we're going through and making changes to various settings, whether it's cut patterns, step overs, things of that nature, we'll get real-time updates with the automatic generation. If you don't like the automatic generation, you can go to the generate pull down that's now available in these operations and select the typical or legacy generate icon, and that will allow you to disable the automatic toolpath generation, and that will then allow you to generate as you've done in the past. Cloud Connect Tool Manager. So this is something that I think a lot of people have been looking forward to. It's a new graphic-based interface to our tool libraries. So we can see that in this new Cloud Tool Manager, the first thing that we're going to look at is the actual new user interface. It's just depicting any tools that are already in the typical NX tool libraries, whether you've created them yourselves or with the out-of-the-box library. We'll take a look at some of this new functionality that we can see in real time as we're making changes to tooling, shanks, holders, that we see the real graphic interface update at the real time. The other big portion of this tool manager is the fact that we can go out to different tooling vendors and download or retrieve their tool data and import it directly into our NX session. Currently, we have 3 tool vendors that are part of this program, being Seco, Walter Tools, and Frasia. So if you're users of their tools, you now can go ahead and directly download information into NX. So now looking at the user interface, we can change some of the views, whether we want to use more of a list type pattern, if we want to see the different icons, what we're calling a card, different summary type views. We can see all the tools that exist in our library and start filtering at the same time. If we want to edit any tool, we can go ahead and edit that feature, and in the different parameters, we can change our tool numbers information, cutter parameters, all the same information that you've used in NX in the past. It's just presented in a different manner. And now we can see it in the graphic interfaces at the same time. You can also delete tools from your library. That's something that was always a little bit problematic, to go ahead and delete tools from your library. Typically, you had to go into your ASCII databases to do that. Another enhancement is searching. You could always do this inside of NX, but you had to know the basic Boolean operations, equal to a diameter, greater than, or equal to, kind of the syntax required. Now we can do it all through pull-down menus, just a little bit easier from a user perspective. Once you find your tool, you can go ahead and send it to your active session of NX. Creating tools is going to work in the same method that we're going to go through and create the tool type, start creating information like your library reference, material type, a little bit more pragmatic approach here in how the dialogues are laid out. Nice experience from the user perspective. Here we can see the tool that we just created inside of our dialog. We've been looking at tools so far, but the same is true of holders. We can now classify our different holders with real holder types that we think of, Cat 40, Cat 50, HSK variants. So we have some expanded capability in how we can search and classify our tooling and holders. Again, the ability to delete. For some users, that's something that has been requested for some time. Being able to delete information from the database up front inside of the graphic interface as opposed to going in text files. You can see here, we're again making edits to our, in this case, holder, and we're seeing the real-time updates in the graphics on the right-hand side. Pretty nice enhancements there. Let's go ahead and jump ahead a little bit in this video, and we'll take a look at this tool expert. We'll be able to go through and see how we can access Phrasea's library directly through the NX interface, in that we can use the different tools that are provided by the manufacturers, the tooling manufacturers, to search their libraries, to find what tools we may want to use. And this will allow us to import the data directly into NX. So that's reducing or removing any chance of error from the actual tooling vendor's information. So that's reducing our chance of issues and helping provide all the information to the process. So now we have tool manufacturer numbers included right with our program that can be included depending on how you like to handle things in your posted code or sent to your tool management software. We'll jump to talking about positioning parts and fixtures in context. Again, this is going to be geared towards those users of NC simulation. So if you've been sticking with the latest versions of NX and you use bounding box or bounding cylinder as your blank type, some of the functionality we're going to take a look at here is going to be very reminiscent of some of the other later enhancements. So again, within the last 2 or 3 releases, we have enhanced the bounding blank and bounding cylinder blank type to be able to position MCSs in relation to the part. We're using the same kind of strategy here with positioning our machine tool or positioning our setup on the machine tool. So, as you're probably aware, you can now show your machine as you're positioning it, change the translucency value. But here we're showing that we have the ability to create a bounding box or a bounding cylinder around our part that we're going to be positioning, and selecting in the part mounting dialog some location that we want to reference to position this on our machine tool. If you're an NC simulation user, you're probably familiar with part mount junction and specifying some location on your fixture or part, and you have the ability to position it to one dedicated location on your machine. This now expands upon that we can use the part mount junction or any other location on our machine tool. So we saw how this can position one part, but where the value of this really comes into play in my mind is once we turn on here, we'll show that we have our a chuck that we're holding our part, we have a fixture plate that it's mounted to, because I really want to position this whole assembly to my machine tool. So now when we go ahead and load our machine tool, we'll see that we have those same options, bounding block or bounding cylinder, and we can utilize that in the context of the entire assembly to position our part. So now we can see that, again, we have those two options, bounding box or bounding cylinder, and in our dialog, we can pick different points to reference, whether it's a midpoint, corner points, midpoint on an edge, anything like that, and then also select a point on the machine. So I think you can see how it would be easy to put multiple fixtures on one part or one machine. A common scenario would be, op1, op2, flip part on a basic vertical machine, or just to orient your part more easily, taking into mind the context of that assembly. So new useful, beneficial tools there for NC simulation users. And again, this works on all machine tools. Here, we'll get rid of our fixture plate and position the chuck and part onto a mill. So again, it's referencing that part mount junction right now. And if that's the appropriate point, we can leave it there or move it around and select some given points that we want to reference and position our assembly appropriately. There we go. We can specify our chuck to our chuck mount and orient the chuck appropriately. So it's pretty new, powerful enhancements there in terms of NC simulation. Automatic tool holder collision. This is regarding turning tools and using tool graphics. Out of the box, if we generate some tool paths in turning, we are always actively checking collisions against the insert. But our insert has to be mounted into something. So here, using a tool graphic with an actual, in this case, C6 holder, we can now automatically check for the collisions of that holder without having to go through the lengthy process of creating this interference geometry, creating cross sections through a tool, assigning geometry to specific layers that you could do in previous versions. This is all going to be handled automatically now. So when we go ahead and generate a tool path, it is going to be checking against our tool holder as well. The real benefit here is we don't have to wait until a downstream process of actually getting into simulation to catch this information. We can see the results kind of in real time as we're generating and colliding with a holder. In this case, we would know that we have to change our approach point so we don't clip the backside of this tool. Some enhancement for our shank creation. So shanks have been available in NX for a number of years now, a number of releases, but we were limited to only 3 parameters. We could have a length, a taper value, and a taper length. So it was a little bit limited in scope of what we could do. So we're going to look now at the ability to have multiple steps in our shank, just like you probably are used to from creating holders, and the functionality that we support deriving all of our step values from a solid body. In this example, we'll take a look at a face mill arbor and how we can create that using data provided from machine tool or tooling vendor. In this case, we've specified our particular insert parameters, and now we're entering in our offset value from the insert stack up to where our shank is going to begin. And now we can select the solid body and extract the parameters from that body to create our shank revolved geometry. And just like any of our tool libraries, we can go ahead and save this shank information now off to our shank library and reuse that shank in other tool assemblies. So the perfect use case here would be the fact that we're going to use the same arbor with different inserts, different nose radiuses. We're going to reuse that multiple times. So pretty powerful tool to go ahead and reuse that data. Another new tool is our dovetail tool. So again, we can use this in some new operations or some different operations like planar mill, Z-level undercut. Again, a dovetail by nature is going to do a lot of undercutting, solid profile, 3D, things of that nature. One, of course, dovetail fixturing has gained popularity immensely in the last couple of years. So a lot of people need to cut dovetails on features just for holding properties. But of course, a number of other use cases. One, dovetail features on part for other geometry, other reasons than work holding. But also these tools can be used for deburring undersides of features, get into a hole and the backside of a hole, cut that type of geometry. So again, very pragmatic feature or tool creation that we can use here. A lot of these things we could do without the specific tool, using a regular end mill with some different parameters, but oftentimes we would have to maybe even create a little sketch of a tool to get the right values. So really just going to speed up your process of being able to define this type of a tool as you're building your dovetail tool library. And again, you can see the different planar milling type operations, 3-axis deburring operation, solid profile 3D, and profile 3D are all going to be supported by this operation type. All right, we're getting towards the end of our session here, and we're going to cover extract operation cut area. I'm pretty confident that anybody that's programmed in NX for some point in time or some length in time can say that they've gone through and programmed an operation only to later realize that they wish they would have created a geometry group to reuse that cut area geometry downstream. Well, now we're able to go ahead and take an operation that's been programmed and cut area has been specified inside of the operation and extract that information. So we'll see here in this particular operation, we're going to right click, choose Object, Extract Cut Area. And what this is going to do is go ahead and create a mill area geometry group with that geometry assigned to it already. So with that being said, we have the ability to create other operations, attach them to that mill area group, enabling us to much more easily reuse those geometry selections without having to go through it and do them an additional time. Just a little time savings effort in that type of an operation. And the final topic for this session is NX on-machine probing. So this is a completely new approach to on-machine probing. NX had the capability to program on-machine probing for quite some time, but now we have this new operation type. And this new operation type is coming from a whole new perspective. It doesn't assume that every NC programmer knows every single probing cycle that's available to you on a machine tool. So the typical workflow here enables us to just select some geometry that we want to probe. And NX is going to give us the options, the cycle options. So in this case, we have a Siemens control on the machine that we have in our setup, and we can see the different cycle types and descriptions of a particular probing operation. So we can go ahead and enter our, edit our probing parameters, and we'll see the different variants or parameters that we would see on the machine tool in the cycle, but now we're doing everything via NX. So in this case, we can change things like our probing safety distances, locations, heights, so on and so forth, generate our toolpaths, and we'll see, and we're able to verify and use toolpath animation to step through all of the motions. So that's great. We did programmed a quick Z motion here, but now if we edit this exact same operation, pick some different geometry, in this case we'll pick some two opposing faces of this geometry, and we'll see that our cycles available to us have changed. We now just have cycle 977 to check measure a rib feature. Again, we can change our probing heights, locations, distances, as well as kind of the intent of the operation. By default, we're just measuring the feature. Maybe we want to set a work offset, at the midpoint of this axis. Maybe we want to measure a feature that's already been cut and adjust our tool comp based upon the results of this probing operation. So essentially anything you can do on the machine tool, you can program here inside of NX now. And we can also see the full animation of the toolpath. That was another gap in the process before. Essentially, we could see the probe get pre-positioned to some location, but we wouldn't see the actual motions of, say, probing a boss or a bore or something like that. Then the next step of this is, of course, we have to be able to post-process these operations. So on Post Hub, we have post layers that can be downloaded and imported into your existing post processors, post configurator post processors, to output all of the appropriate cycles for your given machine tool. So today, with the 2306 release, we have the ability to support Heidenheim and Siemens controlled machines, and FANUC is scheduled to be released within the next couple of months. The other benefit of this new on-machine probing is all the libraries are external to the NX installation. That means as development enhances, new probing cycles are added, you don't have to upgrade your version of NX. You can just go ahead and download the new cycles from Post Hub and use them. All right, so that concludes the what's new for NX CAM for NX 2212 and 2306. Again, thank you for joining us for this session. And if there's any questions, feel free to let us know, and we'll get those addressed for you. Take care. Hello everybody, I'm John Vincent and I'm here for Swoosh NX University covering feature-based machining. So we only have kind of a few points on the table of contents here. Just first of all, what is feature-based machining? And then we're going to look at some best practices for teaching your rules and testing your rules and how to set this up for future enhancements and growth in your processes. So with that, first let's look at what is feature-based machining. This can be considered a lot of different things. It can be considered automated NC programming. It can be knowledge reuse. But in the end, what it is a method to reduce your programming time. So some people say that that's the big benefit, reducing programming time. I think that's a nice to have. But what I see the real benefit is increasing the use of standardization in an organization. So there's not very many prerequisites to start using feature-based machining, but there's really two, the way I think about it. You need to have a tool list, tool library inside of NX of what tools you really have within your organization, and you need to have some agreed upon standard approaches to how you machine individual features. The last part is the challenging one. As we all know, programmer A in an organization and programmer B might do program the same part in completely different ways. Well, feature-based machining is going to cut through all of that, and essentially you build processes based upon individual features. Now you can have a variety of methods for an individual feature. Thinking about do we want to look at PMI information, and if a tolerance is tighter than some determined values, then we use a different process. More of a finishing process versus more just a generic general purpose process. So that speed to have that repeatable or the speed to create programs is nice. I mean, everybody wants to do things faster, but standardization is, to me, what's really important here. And it's no longer in the hands of the programmer to determine how do they want to machine this one particular job that's in front of them, but to have a standard across the board for all parts, material types, varieties for your given organization. All right, so let's dive in. Let's see what is really done here. So in this example, I'm going to be using an environment for feature-based machining. This can be set up in any NX session, but we just have some test parts, teach parts set up that we can use. So Siemens provides a starter kit that anybody can download on Siemens Support Center. So we will, and that really is the basis of what we're going to be looking at here. We're going to be taking a look at some of the out-of-the-box functionality that comes with that feature-based machining starter kit, and how to extend that, how to modify it to make it fit your own preferences, embed your own processes into some default library. So the first step of that is a teach part. So before we get into really looking at modifying your teach parts, I just want to show kind of the end result of feature-based machining. So let's do that. I'm going to jump into NX. Here is my teach part, and in this example, this particular feature, this is a step 4 hole. This has been taught using this teach part. And then I also have a test part. So again, same type of a feature, step 4 hole, different sizes we have here. We also have a couple of features that are different color. We'll use that as an example here in a little bit. But the way things sit right now, I wanted to go ahead and apply some rules and see the results. You might see, I'll even delete these program groups out of here. We have no program groups. We have no tooling. Geometry is just basic structure here. So let's go ahead and apply some feature-based machining. Here, I'm going to go ahead and in the Machining Feature Navigator, I'm going to find my features. In this case, I'm only going to be searching for step features because I know that's what is applicable to what we're working on. The day-to-day usage, you would have any of these parameters that you have feature sets created for. So as I find my features, I find the 3 holes that are in this particular model. And now I can go ahead and apply the feature processes to them. Again, I only am looking at step 4 hole feature processes right now. Well, after I say OK, NX is going to think for a little bit here, and we get this message letting us know that create feature process succeeded, but with some warnings. I can click on show information window and read about those warnings. However, we can just take a look, and if I jump into the operation navigator and generate the ops that were created, we can see that 2 of the 3 features of my test part are being processed with these programs. So right now we don't really know why this other hole was omitted or why these ones were included, but that's what we'll look at next. So I'm going to go ahead and just close my test part for the time being. And in my bearing hole teach part, what we're going to do is look at some of the conditions that have been applied to the rules and process that's already been created. So here, looking at my bearing hole feature group, I'll go into the Teach Operation Sets dialog. And on the left-hand side, we can see that the bearing hole feature has some conditions applied to it. Kind of drill down and look at some of these other operations, we can see there's a variety of different conditions applied to each operation as well. These conditions are making decisions. What tool to use, for example. So in our case, if I read this application condition, I can see that feature diameter 3 must be greater than 20 millimeters for this feature to be valid. So that leads me to believe that feature diameter 3 on that 3rd hole that was not processed must have not met this condition. In order to create these types of conditions, you can see that I could scroll through my parameters here on my feature group and look for diameters. So in this case, if I wanted to create a condition with diameter underscore 3, I could simply select it from the parameter list. The correct syntax is entered for me in my condition field, and I could use the operator conditions of greater than, not equal to, less than, greater than, equal to, so on and so forth, to go ahead and make some comparisons or to check conditions of whether this is a valid feature or not. I can also use the same type of logic to make decisions in the program of what tool is going to be fine, what size tool is going to be applied, things of those natures. So for this example, I want to apply a rule. I want to add another condition here saying that color, the color parameter, if it's not equal to 186, which is the ID number for red in NX, that if my condition, or if my color is anything other than red, I want to apply this whole operation process. So let's go ahead and verify. I'll teach my rules back to the Machine Knowledge Editor, Machine Knowledge Configurator libraries. And now I can go back to my test part. And we'll go through the steps again of finding our features. And once my 3 features are found, I can go ahead and apply my feature processes again. I didn't change any rules about size, so I would anticipate that this hole will still be omitted. However, with the addition of my latest condition, I think this feature, which has been assigned the color red, again, 186 is the ID, I imagine this feature will be omitted as well. So let's go ahead and generate our toolpaths. And sure enough, we can see that this feature was completely omitted. All of the operations that were created were solely focusing on one of the elements of this part. All right, so that's great. We kind of understand a little bit now about applying some conditions. What if we want to expand and do something different for a red feature? Now I'm using color as an example in this demo. However, this could be any kind of differentiator. It could be something like a feature attribute, a face attribute. It could be a PMI note. It could be a PMI dimension with a tolerance, and within a certain tolerance, we're going to do some different processes. For my scenario here, this kind of fictitious scenario, we have our bearing hole process, which is going to be for a default bearing hole feature for us. But however, if the feature is red, instead of milling this diameter 3 to size, I want to mill it undersize and then ream it to finish size. So, in order to do that, we're going to come back to our teach part. We want to teach a different set of rules. And ultimately, I want to do a lot of the same operations. So I'm going to go ahead and copy all of my operations that I have in this part file, or in this feature, and paste them into my bearing hole reamed feature. I'll go ahead and generate those real quick. Now I need to make a couple changes here. This last hole milling operation, instead of milling to size, I'm going to leave 1/10 of a millimeter per surface. And this is going to be stock that's going to be left behind for reaming. Okay, so I've modified my hole milling operation. Let's go ahead and add a reaming operation. So we'll go into our hole making operations, find our boring reaming process. We don't have a reaming group, so I'll add it to my program group for now. Maybe I'll add a reaming group here in a little bit. And I have a reamer in my part that I can use for this feature. Making sure that my bearing hole reamed feature geometry group is selected. I'll go ahead and say OK. And now I can go into my feature geometry group. Just like I was programming a normal part, I would have to make sure I'm selecting the proper machining area. In this case, it's going to be faces cylinder 3. And I can go ahead and generate that feature. You can see that it would be doing the reaming operation. And we'll say OK. And we have two separate processes now. If we look at our program navigator, or operation navigator here, we can see that all of these operations belong to different program groups. And again, all this type of logic is being captured when we're teaching our rules. So let's go ahead and create a new feature group, or I should say program group, and I'll call it reamed. And apply my boring reaming operation to that feature group. All right, so now we have, if I go back to my geometry view, I have a full process to handle whenever I get this step 4 hole with the color red. So let's go ahead and start applying our conditions. I'm going to go to Teach Operation Set. And the first thing I want to do is still maintain that feature diameter 3 has to be greater than 20 millimeters. So I could do this by, again, choosing my parameter and saying that it must be greater than 20. When I choose this yellow check mark, that's checking the syntax of this condition, making sure that everything is valid. I also want to have another condition looking at that color again. However, this time, if it's equal to 186, then I want it to go ahead and process the rest of these operations. So my conditions are slightly different here. Now, we didn't really get into any of the conditions that were applied to the subsequent operations. You can be as simple as you'd like in determining how to make some decisions here, or you can be very detailed Again, it's all about your process, how you actually make decisions on a day-to-day basis. So for an example here, I'm going to go ahead and look for my tool. I need to decide, how do I want NX to know what tool to select? In this case, I want it to look or set the tool diameter equal to, in this case, we're just doing a spot drilling operation, so I'm going to make this a constant value, 12 millimeters. And at any point in time, I can click the Teach Machining Rules, and that's what writes back to the feature-based configurator libraries. I can do the same thing on down the line. Again, in this process, I'm always drilling undersize, so I might want to do something like a tool diameter is going to be less than or equal to, or in this case, maybe I'll just say less than feature diameter 3. That's the smallest diameter on my part. One example. I could very well hard code values in here too, but it's not going to be very dynamic for future operations. So let's stick with our process of setting this to less than feature diameter 3 and apply that rule. By the same token, I might want to look at my tool and set the flute length to be greater than my feature depth. So in this case, my depth is the overall depth of the entire feature, not any one segment. So I'll say to the whole depth, and I'll do some math. I'll add 2 millimeters to that, just to be sure. So that's kind of what it looks like to start applying some conditions. I'm going to go ahead and pop in some the rest of the conditions for these rules. It's really the same procedure here. And if there's anything interesting, I'll come and speak back up and add a few more notes about that. All right, so let's go ahead. I'm going to teach my rules before I get moving here, and here we go. And now for our reamer operation, I'll go ahead and just explain what I'm going to do here a little bit more, because I'm going to have some different conditions in here. I'm going to look at picking my tool, and I'm concerned with the diameter of the tool. And I'm going to say that the tool has to be greater than or equal to a couple different conditions. So I'm going to do add a parenthesis, and I'm going to say it has to be equal to feature diameter 3. You can see that there's a plus sign next to it. I can expand this. So I can say feature diameter 3 plus the lower end of the tolerance. See, it's a negative value. And this to be greater than the diameter plus the low end of the tolerance. And it has to be tool diameter less than or equal to our feature plus our upper end of the tolerance. So now we have two different conditions all handled inside of one line there to make some decisions. All right, so with that, let's go ahead and teach our rules one last time. We'll say OK. And accept those options. And now we can go ahead and look at our test part again. So let's go ahead and do this process again one more time with finding our features. Say OK. And now apply the feature process to all of them. Again, we can see that there's a second process down here. And now with NX finishing up applying these feature processes, we can look back in the program view of the Operation Navigator, and we can generate all of our tool paths. And we'll see that we processed two operations, or two features. So again, that's what we did originally, but we made some changes. So let's take a look. And it looks like I can already tell that I didn't have a reaming operation originally, but now I do have my reaming operation for this one specific part, or feature. Additionally, I made a change between these last hole milling operations for each feature. So let's say the feature on the left has a part side stack of 0. Or if I go to the hole milling operation for the red feature, we'll see it has a part stock of 1/10 of a millimeter. So we're leaving enough material for that reamer to come in and clean it up. So this is how you can kind of slowly build your library. You don't have to sit down and start populating tons of data at one time. You can incrementally start building your feature-based machining libraries with repetitive features. I mean, we want to target the biggest problems first. So the very repetitive features, holes, threaded holes, whatever you tend to make a lot of, start with building the rules there. And then you can expand out to more unique features, different types of pockets, or slots, corner notches, different things, the way that NX names these things. It's also important to understand that if you have unique geometry to your organization, maybe some proprietary design, or maybe NX doesn't find the entirety of a feature as one object. Maybe it finds a portion of some feature as one object and the other portion of a feature as another object. But we have the ability to go ahead and teach features inside of NX as well. So always something to keep in mind to go ahead and reference as you go down the feature-based machining process. Again, I want to stress that it's very important to use this strategy of teach parts and test parts. The test parts are going to have multiple iterations. You want to put different types in there to catch things that are going to be differentiators for you. Again, here we have two conditions on this particular example of using a different color and some different sizes to make sure that we don't fall below some threshold. Additionally, we want to use the teach part process as if you need to make a change. Again, if I had some new strategy that I wanted to replace in my bearing hole operation, I would just come and change these operations or even replace these operations. Maybe I don't want to do a hole milling operation anymore. Maybe there's some new operation that can function much quicker. Well, I could go ahead and just delete all the operations in my teach part, replace them with whatever is now appropriate, reteach these features to the feature-based configurator libraries, and anytime I use them, we're going to go ahead and process our parts downstream. So we can see that we've kind of covered the basic aspects of feature-based machining, and now we can go ahead and you can continue on your feature-based machining journey. Thank you. Hello everybody, welcome back. And in this session of NX University, we're going to be looking at CAM hidden gems. And particularly we're going to be focusing on tool axis control, multi-axis tool axis control. So I think what we're going to do is talk a little bit about just how does the decision-making process go when we're thinking about what operation to use, what tool vector to use. In my mind, it's a little bit of a cyclical thought process there because not all operations support all tool axis controls. Not all operations support all tooling types. So there's a few things you got to think about. What type of a tool do you want to use? What type of tool axis control do you want to use to make some of these decisions? Then we're going to look at some of the, I would say, consider them to be basic methods of multi-axis control, and go into a little bit of an example showing some of the functionality there. So, again, talking about which operation and which tool vector control method should I use. Again, this is kind of goes back and forth. If I know that I need to use a bullnose tool, well, that rules out using a guiding curve operation. It's not supported. If I know I'm going to use a ball mill, then I know I can use surface area drive method, I could use streamline, I could use guiding curves. So how do I decide what I want to do? Well, then I can start thinking about tool vector options. Again, as you get to know which tool vectors are available in given operations, you'll be able to start thinking a little bit more carefully about what you need. The other thing that comes into play is quality of the results versus effort spent programming. If we're working on a part and it needs to have, the best finish possible, I need to get near a mirror finish, or I need to really control, to a high degree my tool axis. Well, then I'm going to probably be doing something more along the lines of interpolate vector. There's more effort from a programming perspective, but also we can expect better results. Now, if quality, is not the primary objective, maybe we just need to make a shape. Maybe it's not a tight tolerance. It's not a, functioning surface that needs a lot of care done to it. Well, then we don't have to spend so much time. We're just worried about executing that geometry and moving on to the next problem. So with that, let's talk about some of the basic methods here. So in my mind, away from or toward a point and away from and toward a line are some very pragmatic approaches to controlling your tool axis. We can change this focal point, again, whether it's above our geometry or below our geometry that we're cutting, same with a line, above or below, and just say that we always want the tool vector to be touching or going through that point or line. And now, in the case of point, away from point or toward point, we're always going to have 5-axis motion. So, 2 rotaries of the machinery. Away from line, you're going to have 4-axis cutting as long as the line that you are specifying, it's really a vector, not so much a line segment, but as long as that vector is along one of the orthogonal axes. If it's not, then you're going to have multi-axis, 5-axis motion. So let's go ahead and jump into NX and just take a peek at some operations here. So we can take a look at this part. I just kind of have a free-form surface on this part geometry. And I have a few operations created already. All of these are variable axis surface drive operations. And I've kind of done some of the different combinations of tool axis control methods. So in this first one, we'll see that toward point, I have, again, let me show, I have a line that I'm using. There's also just the midpoint of this line is what I'm using as my point for my operation. But we can see if I use toolpath animation, let's go ahead and select that operation. We can see that the toolpath looks nice and smooth. And so we might think that we have a great result here. However, with the benefits of having NC simulation instead of NX, we can go ahead and take a look at what is the machine really doing here. So this is one of the tricky things with multi-axis machining, of really being able to visualize what's happening on the machine tool. So in this case, we can see, let's turn off my machine collisions because my coolant lines are hitting here. I'll go ahead, yeah, that's fine. We don't care that they're gouging in there. But we can see that we are certainly cutting this part, and we are doing so with quite a bit of C-axis rotation, quite a bit of A-axis movement. Again, I didn't have to spend much time specifying the tool path here or how I want to control my tool axis. But a good example of, a result that you can have with away from point, or toward point in this case. So you might see, again, a lot of excess motion going on. So again, probably not the highest quality in terms of surface, but it's important to realize that I can also control some of this motion with my point. You can see, again, here's my point that I've specified. If I want to go ahead and offset that point, let's go ahead and just move it up by another 200 millimeters. I can regenerate my toolpath. Toolpath itself doesn't look any different. But when I come in to simulate this toolpath, we can see that we certainly will have a different result. And then we're going to be having far less motion. We're still getting plenty of C-axis motion, A-axis motion. It's just minimized. The A-axis, in particular in this case, is quite minimized because that point that we're projected to is further away. So, again, useful for certain scenarios, certain types of geometry. If you can think about if we were machining down inside of a pocket right now, this might be a great option. Similarly, with away or toward line, we can go ahead and simulate this operation and see some of the differences. Now, instead of toward a point, we're going toward a line. And we can see that now we're not getting any C-axis motions, again, because my line is right along my A-axis or along my X-axis. So we're only rotating that A-axis. That's all that's taking place on this particular part. So again, maybe a better approach. Again, it depends on your requirements. So that's something to always keep in mind. Now, away from point, you can essentially have the same settings. However, the drive geometry or vector geometry, whether it's a line or a point, is going to be below your part geometry. That's the only real difference between the away or toward options. Relative to vector, this is an operation that I see as or a method that I think is underutilized. I don't see a lot of customers using this method, and I think it goes to speak that maybe it's a little bit misunderstood of what the intent of this is. So again, let's jump into NX. I have a good example. This is kind of a single represents a single blade airfoil. And again, let me turn the base of my machine off so we can see things a little bit better. And I have the operation programmed a couple ways here. So the first one is relative to drive. This makes sense to a lot of people that my drive geometry, in this case, is my part surface. And I want to apply some lead and tilt angles. So in this case, I want to cut 10 degrees with my tool, cutting on the leading edge of my tool, so kind of the front edge of my tool. And I want to tilt a negative 15 degrees. In this case, I want to stay away from kind of the floor where this airfoil terminates. And when we simulate, we can see that, of course, just by looking at NX, the toolpath looks nice. It's wrapping around the part as we would want in this type of an operation. However, when we start simulating, we'll see that, yeah, we're positioning and we're cutting, wrapping that C axis around, but we're also getting movement in our A axis. We can see that that's moving quite a bit. I can even pull up my machine status here, and we can see how big of a range. Went from about 70, 80, let's see where are we at here, 90 degrees, 91 degrees, down to about 64, somewhere in that area. So quite a bit of motion in the A axis. If that's not desired, we could look at using relative to vector. Now in this case, with our relative to vector option, we can specify a vector. Again, in this case, it's going to be kind of my z-axis of my part, or in relation to my machine, but going along the axis of the part. And I still want to maintain that 10-degree lead. And this time, because I'm measuring my tilt angle off of my vector that I'm relating this to, it's going to be 75 degrees, kind of the inverse of what we had before, which was negative 15. And now when we look at this simulation, we'll be able to see the difference in the results here. Again, let's bring up our machine status. And now we can see, I'll go ahead and speed this up a little bit, that we're getting our nice wraps in the C-axis. However, the A-axis is not moving whatsoever. Because again, we're positioning that relative to the vector. If I had a vector that was not, parallel to this A-axis, then we would get motion there, depending on the deviation. So it's a little bit of getting used to what the operations are and understanding how you can apply them to your part geometry. No two parts are the same, but the principles of how we use these tools are. Jump back to some pretty basic operations here. Normal to part, relative to part. Normal to drive, relative to drive. So one thing I find, again, that users can struggle with, when I open up a variable axis operation, and I take a look at my tool axis control methods, there's a pretty long list of options here. So this is one thing, in my mind, I think Siemens could do some improvements here on combining things like normal to part and relative to part. That could really be one option. If you do relative to part with no lead and no tilt, then it's normal to part. So I don't see a need to have separate operations. One of kind of a pet peeve of mine. I think this just adds more complexity than necessary. But that being said, so we can understand, normal to part is really just looking at what is my cut area, what am I cutting, and I'm going to make sure my tool is always staying perpendicular to that surface. So as we go through and play this tool path, you see our tool is going to tilt in whatever motion it needs to stay perpendicular to the surface at that contact point. In this case, if I change my operation normal to drive, we'll see that my drive surface is my part geometry. Well, what if I change my drive? I'll make a quick change to my model here just to get some an additional surface. So let me go ahead and jump into modeling. And I'm going to do an offset surface. Let's do a single face here. And now I have just one planar face. And we'll jump back into manufacturing. And I'll change my drive surface from the part. Go ahead and remove that and assign this new surface. Go ahead and set our cut directions. And I can generate my tool path. See, the tool path doesn't really look like it changed. Let me go ahead and hide this surface now. However, now that we are going to change our part, normal to part, we're going to change our tool axis to normal to drive. I have a planar surface as my drive geometry now. Again, the tool path itself doesn't look like it changed much. However, if I animate this part, you can see, hey, this is a 3-axis operation now, where I'm not doing anything. Same thing. Now, relative to a part or relative to a drive is going to have the same behavior that I'm just applying a lead angle. So lead is going to be tilting forward along the path that you're cutting. A lag angle would be a negative lead angle, it would be tipping backwards. And a tilt angle would be tipping to the right as you're traversing along a tool path. So in this case, if I came down into my part and was stepping along this tool path, if I had tilt, it would tip the holder of the tool to the right. Let's go ahead and put a value on there. And now we can see that tilt angle that's been applied. Likewise, if I did the similar setting on a lead angle, now the tool's going to tilt forward at that part. And we can go ahead and with our animation, we can see that we're maintaining that positive lead angle with each direction. So we're changing that tilt or that lead with every zig or zag cutting motion. We're always maintaining 30 degrees. Let's go ahead and run this through simulation real quick. Now this is a pretty hefty lead angle. But we can see that we're going to get a lot of C-axis motion as we're going from, zig to zag cut. That's okay, that looks good. But we have another option in here. Jump on ahead a little bit. Let's jump back to our PowerPoint. If we want to look at using some of these 4-axis normal or relative to part, again, very similar to normal to part, normal to drive. However, this is going to limit things to a 4-axis specific output. So if you had a surface like we were just dealing with that would require 5 axes to stay normal, the 4-axis options will limit along the axis of rotation. But I want to come down and talk about dual 4-axis on part or drive. Again, similar scenarios. This is useful when only when we're using a zigzag type cut pattern. And that's what I'll show here. Let's change our option to dual 4-axis on drive. Again, I'll just, for the sake of example here, quickly play through. And I didn't put any lead or leg. It's just a normal to the drive right now, which is planar, so 3 axes. Now, on my zig cuts, I have the ability to say I want to have a 30-degree lead angle. And maybe I'll have a 15-degree tilt. And then on my zag cut, I can have different settings. So if I would type in 30, this would be the same as doing just a regular normal to drive or a relative to drive. But I can do a negative 30-degree lead and a 15-degree tilt. And we'll see the difference here when I go and generate this tool path and simulate. We'll see that we're going to get far less motion. In fact, we're only getting just that small amount of C motion here for the tilt that's changing. So essentially, we're moving 30 degrees with each zig or zag pass. But we're not changing our lead angle at all. It's a negative 30 degree on a zig cut and a positive 30 on a zag, or vice versa, actually. So just a little bit interesting here. I could, in theory, change from a positive 15-degree tilt to a negative 15-degree tilt on the zag cut. And the result is a 3-axis cut, just a regular 3+2 operation. So again, understanding how you can apply and utilize drive geometry along with lead values, tilt values, things like that become important. Of course, we have some more complex options available to us. One of them being one of the popular ones, and something that's definitely worthwhile learning, is interpolate vector. You can have immense control over your tool axis with interpolate vector, but it also requires a lot more effort. Essentially, what we're doing, any drive surface ultimately has 4 system-generated vectors, and they're all at the corners of your drive surface. Those will be there anytime you're using the surface area drive method. And you'll get some vectors there. Now, you can modify those vectors. You can add points and include extra vectors. There's really no limit to how many. But what the software is doing is interpolating between those points. So you can have some nice tool paths that fan very smoothly. You can have tool paths that change very abruptly. So again, if we look at I'll open up my operation with interpolate. There we go, with interpolate. And we can see I have just 4 vectors at the corners, all kind of pointing in towards the part. So this is going to have a very similar result as a toward point. If I have some point that I'm projecting towards, essentially there is some point that all of these vectors would intersect at. Now, that being said, we can change things differently, independently. So here, maybe I'll set my Z normal to a surface. Let's find which vector. Here's this one. So I could start being normal to the surface and then interpolate to being, have a tilt or a lead angle relative to that surface. Lots of different options. We also have different interpolation methods. You want to wait to interpolate until you actually hit that point on the vector. Let's see if I added some additional point in the midpoint region here and just move at that exact location. Or do you want to use a smoothing method? Have a nice fan between those options. So there's lots of different things you can do with interpolate vector and really have some very finite control over them. Let's go ahead and just run the simulation here, and I'm going to jump onto a different part and show a little different example. Again, kind of have a similar result as what we had with away from point. However, now 2 of our vectors on 2 sides of the part are in a different location. So we're not getting so much excess motion in there. So let's take a look at another example here. I want to show a couple more things. In this case, I'm going to create an operation, and I want to cut this blend. It's kind of down inside of a pocket. I think this is a good example, real world example of things that we have to do. And oftentimes people use just extended length tooling to reach down in there in more of a 3-axis method. Let me go ahead and create a toolpath. I'll use a guiding curve operation. And let's see here. Go ahead and create that op. I need to pull a tool in. Let me go ahead and measure that radius. 3 millimeter radius. I'll get a 5 millimeter ball end mill. So we're actually going to be cutting that blend, not just forming it with the tool itself. All right, there we have a 5 millimeter tool. I'll go around and specify my cut area. And I'll use one of these new methods here. Let's see, we'll do morph around mid-pass. Do a helical pattern. Yeah, that all looks good. And our default axis method is normal to drive. Let's go ahead and just say OK and generate. All right, so we've generated our toolpath. If I were to come in and play the animation here, it becomes apparent very quickly that, yeah, our holder is going to gouge with this part. So this is a spot where we could use away from point and then change the height of the point to influence our toolpath. Or we could use interpolate vector and manipulate all the vectors to clear. But here on this part, this is something that I don't really want to spend that much time on. I don't think we need to. Let's use some other functionality that's inside of NX. On the axis and avoidance page, we have this axis and avoidance and axis smoothing. The default option is just set to report collisions for most 5-axis operations. But we can also use this tilt and retract option. So tilt and retract will look at your clearance values set in the operation. I'm going to accept these. I'll talk about some of these settings in a little bit here. But these clearance values, clearance of our holder, our shank, and our tool neck. When we apply the tilt and retract avoidance method, it's going to honor all these settings. I'll go ahead and generate my toolpath again. Now we can go ahead and animate this path again. And we'll see as we come down the path, we're going to start tilting before we get to that part geometry. So we're going to be honoring those clearance settings so our tool never collides with our part geometry at all. It's a pretty nice option using that tilt and retract option inside of these 5-axis operations. That same functionality can be used elsewhere. Let's look at finishing kind of this tapered, canted wall. And maybe I'll even do this in a different method. Let's use a fixed axis operation. I'll use a fixed axis guiding curve. Still use that same tool. And let's see here. Let's just do offset around end pass. That'll be fine. Do zigzag. All right, so with that, we can see, again, we can play our simulation or our animation here. Let's jump down a little bit. And same scenario. We're going to see that we'll have collisions with our holder. So let's go ahead and use our functionality to go ahead and tilt our tool axis. We might consider this like converting 3-axis toolpaths to 5-axis toolpaths. So with that being said, I could go ahead and just say, use the manual tilting method, just set this to keep original, look at our collision values. Let's take a look at the result. We want to step in and start playing this toolpath. I'll jump down a little bit further. And we can see that we're going to start getting some leg angles in our toolpath as we're cutting. So we're staying away from that wall. We can also do some additional settings on top of that. Let me come back to our tilt tool axis page. And under tilting, we could do user defined. So I could do something like apply a reference, in this case, just a ZM direction. I could change and stay away from certain curves. Again, this is going to be curves, like edges of part. I could create a sketch that I need to stay away from or toward, away or toward a point. Or I could do some fixed settings. Maybe in this case, I wanted to add 15 degrees of tilt. Now when I start my toolpath, you'll see my tool's already tilted 15 degrees. And I can start playing through here. Let's jump down. We'll see that we're going to honor that 15 degrees of tilt all the time and still clear as we get near the corners of this part. So a lot of different things you can do here with the tool axis tool set to go ahead and improve your 5-axis toolpath programming. Again, goes back and forth between balancing of the quality of the surfaces you need, the amount of control you need, the speed at which you can create these programs. And the big benefit is we have the tool set to do all of these different options inside of NX. So that being said, that concludes the hidden gems for NX CAM here at NX University. Thank you, everyone.
Hello, everybody. Thanks for joining me on this session for the NX Measure tool. This is something you can consider to be really a kind of a part two of a series of measure sessions that we've done. In last year's NX University, we covered some measure commands, and due to popular demand, we had some questions on covering even more different ways that you could use the measure tool. So we're going to go ahead and go through some of that here today. This was originally set up to be a hands-on session, so I'm going to be walking through some activities, different examples of using the measure tool, and if you're available to run NX at your location along with me as I go through some examples, then I very welcome the follow along if you want to go through that with me. But also, if you just want to sit back, relax, and just watch the demonstrations, you're welcome to do that too. So as some of you might know, the measure tool had been enhanced several versions ago to combine a lot of different individual measure tools. Like there was a distance measurement and an angle measurement. A lot of those things were combined into one comprehensive measure tool that can do a lot of different things. And some of those are kind of easy to use. Some of those maybe not so obvious on how to go through that. So we've done a series of measure demonstrations on how to use the tool in different ways. And I think in the past we've done some of the enhancements like the chain measurement, for example. So we're going to kind of pick up on some new use cases through the measure tool. And before I do that, let me introduce myself so that you kind of know who I am and invite you to reach out to me if you want to. So my name's David Chu. I'm with Switch Technologies. I'm based in St. Louis, Missouri. And my current title here with Swoosh is as Customer Success Manager. So I'm responsible for making sure that our customers are successful with the product. That's basically what my role is. But I've also spent many, many years in a technical role. I've been in technical pre-sales. I've been in educational services. I've been in professional services. So I've done a lot of things like, present NX and Team Center demonstrations. I've conducted training classes in both NX and Team Center. I've helped to deploy and basically installing and configuring Team Center. So if there's anything that you think I can help you with, feel free to reach out to me. You see my email on the screen as well as my phone number. You can also connect to me on LinkedIn if you like. There's my QR code. That'll take you there. And feel free to contact me. So just briefly explain the activities that we'll go through in this session. So we've got about 45 minutes or so. And we've got 4 activities that we should be able to fit into this time frame. The first one is going to be on finding point coordinates. So we're going to take a small assembly and interrogate different locations on the assembly and find out where those point locations are relative to a particular origin or coordinate system. So we'll be able to take a look at how we can define coordinate systems to get some meaningful values there. The second activity is going to be showing how to take directional measurements. And by that, we mean being able to specify a vector and measuring along that vector. So it could be the X, Y, or Z direction, or it could be a vector that is being defined on the model. If there's a line or an edge on the model, or maybe a couple points that you want to measure a vector with, then we'll take a distance measurement along that vector. So that's number 2. The third activity is going to continue on with working with an individual part. We're going to be taking a look at the basic mass properties of a part and finding the weight and the volume. Volume is getting more and more critical these days because of the popularity of 3D printing. So people need to know how much material they're going to use. But something else that is also helpful for 3D printing is finding out the bounding box size. So a lot of our customers that have multiple 3D printers, they'll have different capabilities, different envelope sizes that the printers can handle. And, they'll be looking for the bounding box size. So I want to show you how to get that. Some of you might be familiar with the bounding body feature. So there's a bounding body as well as a bounding box, 2 different things. So I'm planning to show you the bounding box that's part of the measure tool. And the fourth activity we'll get into is going to be taking a look at getting assembly mess properties, and we're going to introduce a visual report here in this example. because actually generating mass properties for an assembly is not too much different from a part. But part of the challenge of getting mass properties for an assembly is making sure you've got all of the materials assigned properly for that assembly. So we'll be also looking at a visual report to find out where we might be missing material information and making sure we've got all the individual mass properties updated in order to get an accurate assembly mass property value. Now, in this fourth activity, we're also going to be taking a look at a tool that's available if you have a Mach 3 CAD license. In that bundle, that includes advanced assemblies. So within advanced assemblies, you'll have another panel in your assembly navigator that will be a tool that you can use to easily browse through mass properties in assembly. So I'm going to show that to you. Everything else I'm going to be showing is going to be based on capabilities that are part of the standard modeling license. But when we get to that point, I'll try to remember to remind you that what I was going to be showing there with the assembly mass properties panel within the navigator, that that does require a Mach 3 license. So let's go ahead and get into some demonstrations. All right, hopefully you can see my NX window here. I'm running NX 2306 4000. I think there's at least a 7 or 8,000 update that's available here. So let's get started. Like I said, the first activity is going to be on finding point coordinates. So the first thing I'm going to do is open a small assembly here. So before I do that, let me check my load options. And let's see, at least we want to do a partial load. Yeah, I think that's going to be good here. So let me go down here and open up our assembly. We want to open up this axle support PT assembly. Open that. So here you have a small assembly. If you take a look on the left-hand side, there's maybe a dozen or so components in here. Most of those are fasteners, but we've got a couple of primary parts. You see the green main body here, and there's a yellow, like a lug on the right-hand side. So before I do anything, I'm going to go ahead and reset all the dialogues. With NX likes to remember all of your settings from previous work that you might have done. So let me go ahead and reset that. If you're not familiar with this, just go to File Preferences and go to User Interface. And then pick, on the left-hand side, pick Dialog and Precision. And you'll see a button here to reset dialog memory. So this resets all of the dialogues throughout NX back to their default values. You can, of course, reset each dialog as you go, and I'll show you that as well. But this will take care of a lot of them right up front. So just hit the reset button there. Let's click OK and move on. All right, so we're going to be working primarily in the analysis toolbar up here. So if your analysis toolbar doesn't look like mine, it's most likely because you're working in a different role than I am. So I'm working in the advanced role. So just to point that out down here on the left-hand side in the resource bar, if you take a look at the roles tab, I've got the advanced role active. So just to be sure, I'll go ahead and click the advanced role again and see it's going to give me pretty much the same toolbar they had before. So I'll remind you about that again later on as we go through here. So the measure command is going to be over here on the left-hand side of the ribbon bar. Open that up. And again, up here, if you didn't do the reset before, you can always reset individual dialogues with this icon here towards the upper right. There's the reset, that circular arrow. So if you just hit reset, you'll get to reset your dialogue there. All right. So the first activity is on finding points. Maybe we want to find some point locations. If you take a look at where the work coordinate system is down here, that might be a convenient reference. So let me start off with a measurement of points using some of the default settings here. So if you want to measure a point, then take a look at these settings up above. These are all different radio buttons. So when you pick one option, it overrides the previous one. So we're going to go ahead and select a point to interrogate. Set the point option. You've got your snap point options here. Just make sure that the point that you want to select is going to be eligible based on the option that you have selected up here. So let's say I want to have the coordinates of this point here at the top. So I'm going to select the arc center there. And you'll see it immediately gives me an answer. And if you take a look at the numbers here in the banner, you've got X, Y, and Z. And, relative to our work coordinate system, those numbers don't necessarily make a lot of sense right now. So first thing I want to point out is that right off the bat, if you're taking point measurements, the coordinates that you're going to get are going to be based on absolute, not work, not any other specified coordinate system. So if you have your hints enabled in the measure tools, you might see a hint down here, and this one is really pertinent to what we're trying to do here. The second one for a relative point measurement, select or define a coordinate system using the CSIS option. So there's a couple ways to do that. I'm going to show you both ways. One way is to go down here into the settings tools, and you'll see there's an option for reference coordinate system. And again, by default, it's set to absolute. So you can switch this to WCS. And without clicking anything else, you could go and take a look at the values for X, Y, and Z that are reported here. We got 0, 0, and 178.3, which does seem to make some sense relative to the work coordinate system. So that can be helpful. But one of the things you'll see if you take a look at the results up here is when you're taking a measurement relative to the work coordinate system, like a lot of other things in NX modeling, if you're using the work coordinate system, it's not going to be an associative measurement. So you won't be able to save that. This is really going to be for informational purposes only. So that might not be what you want to do. You might want to save an associative measurement relative to a coordinate system here at the bottom of the part. So you can take some steps to create a coordinate system down there. I'm going to show you how you can create one kind of on the fly and have it saved with the measurement. So let me set this back to where it was, set it back to absolute, and see the numbers change again. And let's kind of go forward here. I'm going to collapse this dialog for a moment just to make things look a little cleaner here. And if you remember that hint, it did say that we could use a coordinate system as a reference. So up at the top with the point selected still, we don't have to start over. We can go ahead and click the CSIS option up towards the top, and we're prompted to select a coordinate system. So I'm going to open up the CSIS dialog, and you'll see you've got your dynamic CSIS available. This is your standard CSIS dialog. I'm going to go down and select coordinate system of object. And as a reference on the bottom, I'm going to choose the arc at the bottom of that hole. So let's pick that one. So I'm going to select that arc. Of course, the arcs have a coordinate system. You'll see it appear here in just a second. But before I get there, I just want to kind of point out here, we get a message that says that this selection is going to be added to the work part as a wavelength. So I am working in an assembly. The geometry I'm selecting is coming from a component part. So if I choose to save my measurement as an associative feature, I'm going to get a link to that geometry. So I will get this link created for me on the fly. So really all you need to do here is just accept that. So you'll see that coordinate system show up. I can turn the work coordinate system off, hit the W key. Maybe I should have done that before. But anyway, you'll see the X, Y, and Z directions there. And go ahead and click OK. And you'll see the numbers update. So you've got 0, 0, 178.3. So I'll go ahead and let's save those. So I'm going to go ahead and click to create an associative measure. And I'm also going to click this other option to save an annotation. So I'm going to get a label that's going to be out here in the graphics. And let's hit apply. So there's our measurement right here. You know what? I'm going to cancel this, and I'm going to go ahead and select it. I want to show you. I am going to turn the work coordinate system off. So let me go ahead and show you if I click this measurement. See, it does remember the coordinate system. See that down there in the orange? You get your X, Y, and Z. So those numbers that you see there are going to be relative to that coordinate system. All right, so let's go ahead and do another one just from the start. Make it maybe a cleaner pass through this process. And I'm going to do it in a different order. You don't have to select a point first and a coordinate system. You can select a coordinate system and then a point. So I'll do the same thing here, but this time select the coordinate system first. And let's go down to C system object. I'm going to select that same park down there. You see the preview of the coordinate system that shows up. And then I'm going to go back and select the point. And this time let me select the arc center at the top of this hole over here to the left. And there are my values, minus 91, minus 65, 120.15 millimeters. That's going to be from the coordinate system here at the bottom. So I've already got the option to save the associative measure and create the annotation. Click OK, and there are my point locations there. So these are going to show up. Take a look at your part navigator. There again, there's the linked composite curve. That's the arc at the bottom that's coming from the green component. Then I've got my two measures. So those are going to be out there. You don't have to save those annotations if you want. If you have a measure down here, look at the details. You'll see the values down here as well. So you don't necessarily have to save those annotations if you don't want to. But if you want those numbers for reference, or if you want to feed those back into another expression in another modeling operation, especially if you want those to update, then you do have to make those associative measurements. I just wanted to run through that. Hopefully that makes some sense. Again, the key thing here is just making sure you got the proper reference. If things don't make sense at first with the numbers, it's a good chance that you've got it set to work from the absolute coordinate system. So that's what I wanted to show on that first example. We could spend some time to make some changes and watch those measurements update. That's a pretty standard feature within the measure tool. I'm not going to spend the time here on that one. I'm going to move on to the next example here. So in our second activity, we're going to be taking a look at directional measurements. So to do that, I'm going to open up a part. So let's go and we'll get another part. We're going to get a link lower part. And if you got one of your own parts, you can use that. If you've got a copy of our training parts, you can use that as well. I've got something turned on that I really don't want to turn on just yet, but just ignore that little red symbol out there. That's the center of gravity of this part. I've got something turned on that I didn't turn off earlier, but we'll ignore that for right now. So I've got my part here, and we're going to go ahead and take some measurements between some holes. We want to find the distance from one of these holes on the left to one of these holes on the right, and we'll see how that works. So I'm going to reset the dialog, and then take a look at doing another measurement here. So I'm going to leave this setting set to objects, so I can literally select any type of geometry, either an edge or a face or a point. So I'm going to go over here to the left and select this edge. I'm selecting an edge, and as you probably know, it's going to give me an answer based on what I've selected so far. So it's giving me the sum of the values relative to that edge. I'm going to go over here and select an edge at the top of the other hole. And by default, I'm going to get a minimum distance, kind of as the crow flies, from the closest point on one edge to the other. So it is an edge-to-edge measurement. Now, if you're interested in center-to-center measurements, you can do something different. You could reselect, and you see the center lines that appeared there. You can select center lines to measure between. Or you can go into the menu that shows up in the results banner here. There's a drop-down menu, and you can also say center-to-center. So it gives you a center-to-center, but it's still a straight line distance. It's not along any particular direction. It's the shortest from center point to center point. So without changing things, you could go into the settings dialog, there's a couple things that you can do. If you wanted to know what the X, Y, and Z measurements are in those directions, you can go under settings and you can click the preferences icon way down here at the bottom. So under the preferences, there's different categories here. So if you choose measurements and then look at the distance preferences, one of these options down here below is X, Y, and Z delta distances. And it happens to be turned off. You got a lot of other things turned on, but these are turned off. So if you check that box, click OK, you're going to see those values are going to be added to your results that show up here in the graphics window. So these are available also from the drop-down menu in that banner. So there's a little arrow here towards the lower right-hand corner. If you click that arrow, you can turn off and on different values that you want to see. So we can turn that off if we want. I want to show you a different way to get those values because as you see here, the delta X, Y, and Z distances do not offer you the values that you can save. If you point to that and you see the message comes up as the value says it's informational only and cannot be saved as an expression. So it's fine if you just want to know what the numbers are. If you want to save that value, we're going to do something different. So let me turn that off again. So let's do start over. We're going to go from point to point this time. So I'm going to do a reset in the dialog. I'm going to go ahead and turn off the math properties. Let's see. I got to go down in here. Give me just a second here. Let's turn off these options. Let's turn off the math properties here for a moment. Here we go. I didn't want that to be distracting, so sorry about that. So let's go back in and do another measure. And this time we're going to go from point to point, kind of like what we did before in the last activity. Pick the center point of one hole, pick the center point of the second hole. We get our distance there. This time we want to go ahead and choose a vector. So, we've used coordinate systems before. This time we're going to use a vector. And let's go ahead and choose, let's say, the Y direction. Grab this one. And we're going to get a measurement in the Y direction. So you see it just goes straight over there along that vector, 193 millimeters. And I can save this as a measurement, of course, if I want to. Actually, let's go ahead and do that. And let's go ahead and save an annotation. Let's click apply. We got that one. So then we can do that again. And again, we can select these references in different orders. So I can go ahead and select the vector first. Maybe I want to select the Z direction this time as my reference. And then again, we'll just go point to point. Go from the center point of the first hole to the center point of the second hole. And now I get a measurement in the Z direction. So that's how you get your directional measurements. Hopefully you didn't see too much difficulty with that if you're following along with me. I'm going to go ahead and save that one as well. Just click apply. Now I've got those two measurements. If I do go over here and take a look at my part navigator, just like what we saw before, we've got these measurements added to the model history. Okay? So those are the directional measurements. Let's go ahead and move along here. I'm going to stay with this same model here and get into the third activity. So in this third activity, we're going to be looking at mass properties. We've been able to find point locations. We've been able to find distances using the measurement tool from a couple different objects or points. Now we're going to take a look at body measurements. So let's go into the measure dialog and we're going to reset this. Let's go ahead and click the reset button. Now, if you take a look at the results over down here, I want to point something out. You've got all these different types of results. You've got distance results. You've got curve edge, kind of a arc length kind of result. You've got angle. You've got face measurements. You've got body measurements. So all of these that you see that are shaded in the orange, these are all active results. If I go and select something else, I'll get some answers. That's what's giving you the answers as soon as you select something. So I've got my selection filter up here set to object. I'm going to go ahead and select an object, which is going to be the solid model. This particular part already has a material assigned to it. And I'm going to get into that here in a little bit in the next activity. But for this particular purpose, that's something we don't need to worry about. The material's already been defined, so we're just going to go ahead and pick the solid body. And based on our settings, we've already got some results. We've got surface area, volume, mass, and weight. And we can go ahead and get a lot of other answers here. If we go down into the drop-down menu, you can get moments of inertia, you get products of inertia, rates, gyration, principal axes. If you're doing some kind of dynamics analysis, you might need these values as well as just the the basic weight, volume, surface area. Maybe you don't even want surface area. So you can still change your results there. If you want to go into the results filter and take a look at what we've got there, it says we're displaying one of two measurements. So what does that really mean? If you pass your cursor over these individual icons, it tells you what that measurement represents, but it also has a number in parentheses that tells you how many results it found in that category of results. So you can pass your cursor over these. Eventually you'll come over here and you'll find out that there's a body measurement, which is what we see on the screen right now. The body measurement, and you can tell, if you click that box and unhighlight that, that results banner disappears. So even though there's multiple values in here, that is one result. Now, if you continue on, you've got some extreme measurements, and you've got another kind of vague category called others. And you see there is something there, but it's not being displayed right now. And this is where the bounding box comes into play. So if you do click this to display that result, here's where you see the bounding box. So when the bounding box comes up, actually, let me turn off the other one so it's not so confusing. All right, so here's the bounding box. It's under the others category. So it gives you the full extent of a box that would fit right around this part in the X, Y, and Z directions. And you'll see length, width, and height, X, Y, and Z, and the total volume. So that's what this box represents. If you go over here and we can save this. You know what? I'm going to do it this way. I'm going to go under settings. Instead of trying to click all these different buttons here, you can do it all in one fell swoop. You go over here to the associative option under settings. Let's go ahead and make that associative. We don't need to display the dimensions, but at least let's create the box. Let's create the box. So that is going to be an associative box. You'll see it's going to show up in the model history. If you point over here, see it says create geometry associative to the measure feature. So let's go ahead and do that. Let's go ahead and click OK. And if you take a look down here, and I'm going to expand the part navigator a little bit so we can read that better. It's the bounding box. So it's given to you right there. If the part is to change size, that bounding box is going to update. And you saw the note, it said it was associative. I believe if you go into the details, it gives you the size. So you don't necessarily need to have, you can put the annotations out there in the graphics, but you really don't need it if you just want to get the values here. Now, it's not part of the measure tool, but I just want to point out, if this is just kind of a wireframe box. You'll see if I point here, there's not a face there. If you do want a solid body that represents the boundary of your part, that's going to be a different tool. That's going to be under, if you're in modeling, it's going to be under the More drop down. This is the gallery under the base group. And you'll see there's bounding body there. I'm not going to get into that because this is about the measure tool and it's not about modeling features. But bounding body is going to be a modeling feature. It's going to put a solid box around your part. It's going to be associative too. I just want to point that out. But with measure, you're going to get a bounding box. So that's what we've got there. I think that's all I wanted to show you in that activity. So we're going to move on here to the last one. So in the last activity, we're going to work with assembly mass properties this time. So let's do this. Let's close everything. So I'm going to close all parts. I don't need to save anything, so just click close. And we're going to open up assembly. So let's check my assembly load options. All components partial load. Reference sets are good. Okay, so I think I'm good to go there. And I'm going to open up this thing called a measure assembly. So if you've got our own training parts, you can follow along with me, or if you've got one of your own assemblies, the steps I'm going to go through are going to be just as relevant. So you can experiment with one of your own if you want. So here's my assembly, and you can see I'm going to go ahead and expand this. I know how big this is, so it's not going to be super risky to expand all my components. It's not going to lock me up for a while. But I just expand everything so you see how many parts I got here. If you look at the total count, I got 53 parts. So that's components plus sub-assemblies in this assembly. So it's not a lot, but it's not a super small assembly. So if we're going to take a mass properties measurement of this assembly, the values that we're going to get is going to be dependent on all the parts having the proper positioning, of course, and also it's going to be dependent on all the materials being assigned to the parts and their respective mass properties updated. So fortunately, that's fairly easy to do. If you take a look at the analysis toolbar, over on the right-hand side, we've got, tools for updating mass properties. And we got a report over here that we can run. I'm going to show you how to do that here real soon, just to make sure we've got all of the proper materials assigned. So we've got our assembly opened up. Without those tools, you can go into the assembly navigator, and if you go into the columns, you can turn on columns for the mass, so you can get the mass in terms of kilograms or pounds. I've got kilograms now. Let's switch to pounds for fun. And then also, you can actually have a column for material. That's one of the ways that you can verify if you've got material assigned to all of your parts. Just look at the navigator and see what's missing. So if you haven't done this before, you can go into the configure option. It's all the way down here at the bottom. Choose configure. And then you may have to go into your attribute column selector. Let me kind of start from scratch. Material doesn't show up here as a column that you can pick right off the bat. You got to go into the attribute column selector down here at the bottom, and then choose material. Oh, did I add it already? Let's try that again. Attribute column selector. There it is, material. It was grayed out before, but now it's there. So we got NX material there, and I'm going to move it towards next. Just drag it up towards the top here, so it's easy to find. Put it way up there. So there's material. So you can kind of skim through the list here. For a really large assembly, that can be kind of tedious. It's subject to errors. It's going to be as good as your eyes are in catching these things. So fortunately, there is a report that you can run. It's part of the HD 3D tools, the visual reporting tools. And it's included within the analysis toolbar over here to the right. So we could probably do and maybe we probably will do a future NX University session just on these visual reports. There's lots of different reports in here. As you can see, I'm just going to scroll through probably dozens of different reports. So one of the reports that we're going to want to run here is going to be the part materials report, this one here. That's going to color code all the parts within the assembly and show us what materials each of them are, and it's going to display that on the screen. So we'll run this part materials report, and so it's really a matter of just selecting the report name and then clicking Activate Report. And it goes through and identifies all of the parts, takes a look at the material attribute, and then color codes them. Here's the legend that comes up on the screen. So let me open this up. You see there looks like there's about 1, 2, 3, 4, 5, 6, 7 different materials. And if you take a look at the assembly navigator, you'll see that the report results are also inserted there, so you can take a look at all the different parts within the assembly structure and by color and also by property. So if I compare that to the NX material that I added earlier, they better match, which they do. But if I go back over here, you can see which parts have a material assigned. The empty boxes pertain to parts or subassemblies that do not have a material assigned. So at the assembly level or subassembly, you wouldn't expect to have any parts that, or I'm sorry, any assemblies that would have a material, but there should be some parts that, may have a value missing there. So once again, you can kind of skim through and visually inspect that report column there, but you can also manipulate the graphics within the results here. So if you wanted to hide, for example, all the parts in the dark blue, that's this titanium, you can right click and choose hide. So you can go through and browse the different materials. You can hide different groups here. And ultimately, you're going to end up seeing that there's going to be possibly one or more see-through parts. Let me go through that. So this particular part does not fall into any category. The ones that are de-emphasized, that are kind of see-through or ghosted, this is how you can find the parts in your assembly that do not have a material assigned yet. Okay, so let's go ahead and assign that material. So I'm going to go over here to, in modeling again, if you go to your tools, you go to assign materials, and go ahead and select that part. Oh, you know what? I need to make this part my work part first. So let's make this the work part. All right, so now let's assign a material. Here we go. And, if you're following along, you can assign, have some fun, assign whatever material you want. I'm going to, let's see what I want to use here. It's kind of goofy here. Let's just make it out of iron or something. Probably not something you want to use for a aerospace part, but like I said, we're just kind of playing around here. So I'm going to assign iron to that. Click OK. And then notice I did that with the report still active. That's how visual reporting works. You can run any report and get your geometry color-coded, categorized, and all that. And as you work, you can get the results to update. So within this dialog here, or also within the columns here in the navigator, you can right-click and choose Refresh the Report. So it'll update the report. Now it found a material assigned to that part. If it's different from any other material that it found before, it's going to introduce a new color. So now I've got that part in there. And everything should be fine. So all of my parts have materials now. So I'm going to go ahead and deactivate this report. So it's going to disable all the colors, go back to their normal colors for the assembly. I need to go ahead and, if I go back to my View tab, let's show everything. Get everything back on the screen again. And let's make the assembly the work part. So we went through and did a little bit of validation there using a visual report to make sure all of our parts have materials assigned to them now. So at this point, we're ready to go ahead and do our assembly mass properties. So one of the things that we can do, if I go back to my analysis toolbar, is go ahead and update the mass properties. So if I go back over here, let's take a look at the mass columns here. There's a lot of parts that do not have the mass updated yet. So let's do that. Let's update mass properties. So we're going about this a different way. We're not technically not using the measure tool here. So we've got our updated results. All the parts have got the mass properties updated. You've got some of the roll-ups or sub-assemblies, and of course the roll-up to the top. So this sub-assembly weighs 27 pounds, 12.3 kilograms. That's another way that you get your mass properties. You don't technically have to use the measure tool, but you do use the analysis tools here. Now, the last thing I want to talk about is An option I mentioned before that it does require the Advanced Assemblies license, which is part of the Mach 3 CAD bundle. And that's this tool called the Mass Properties panel. So I'm going to go ahead and turn this on. If you don't have access to a Mach 3 license, if you're following along, you might not be able to take advantage of this. So you might want to just look and see what I'm doing here. But with the Advanced Assemblies license, you've got the Mass Properties panel that can be displayed down here. Normally you don't see this panel in your Assembly Navigator, but now it's here. So when you turn that on, you've got mass properties that are going to be displayed for whatever you have selected. Now, in this case, I've got my assembly of the work part. So you see my mass properties are going to be relative to the assembly, all 53 components. The green check mark over here means that it's been updated. If you don't see a green check mark here, there's an update button that's provided for you in this panel, which really works the same as the update option way up here on the ribbon bar. So if I were to pick a part, let's select one of these parts. Grab one here. Okay. I'm going to select it from the graphics, but let me just go ahead and select it from the navigator. So from the navigator, if I select a subassembly, now see I've got 4 components, and it shows me that result for the mass properties. If I select a rod down here, I got 1 component, which is the main tube here, and you'll see I've got all of my mass properties down here. Now some of these, like if you wanted to find center of mass relative to the work coordinate system, you have to expand those to see those values. So some of those are going to be collapsed just to simplify the display a little bit. So that's how the mass properties panels work. Now over here on the right-hand side, you've got some options. So if you go into the options, this is what I had turned on before from a previous pass through this exercise. If you wanted to see the center of mass symbolically in the graphics, you've got the values that show up in the results, but if you want to see the symbol that shows up, you've got a number of options here. If you want to see the center of mass for the displayed part, you can check this option, and you'll see a red symbol show up. That's what you saw on my screen earlier. If you want to see the center of mass for any selected part, you can choose the third option there, and it'll show up in blue. So I'll show you how that works. So there's the symbol that represents the center of mass for the entire assembly. If I just wanted the center of mass of this part here, you'll see I've got a blue symbol there. If I want to see the center of mass of this part over here, yeah, I don't see it. There it is. Okay, got one there. Oh, I know why. Because I didn't turn that option on. There's an option for selected components combined. So let's do that here. So if I select more than one, say that one there and that one there. Yeah, so that's the result that you see there. So each individual part has its center of mass, and then the green symbol represents the center of mass of those combined parts that are selected there. So I wanted to show that just to give you an idea of some of the other advanced things that you can do with the mass properties panels. That part of the analysis tools, it's not really part of the measure tools, though. But turn those off. So that concludes the 4th activity. That's kind of all I wanted to show here. And hopefully I was able to show some things that you might not have seen before in the measure tool. Like I said, there's a lot of things that you can do in the measure tool. There's probably more things that you can explore and find out how to use within that measure tool here. So hopefully you found this information helpful. And at this point, I'm going to go ahead and finish up here. And if you have any questions, you can feed them into the chat, or if you haven't been doing that already, and we can address those. So let me go back to my conclusion here. So once again, be happy to answer any questions that might come to mind a little bit later on. You can reach out to me either by email or call, but I would say chances are you have a better chance of reaching me through email. So um, feel free to send any questions if you have anything that you'd like me to follow up with. Otherwise, hope you enjoyed the presentation. Hope you have a good day.